Hi, welcome back. In this lecture, I would like to introduce Meep, that is a widely used electromagnetic solver based on the FDTD technique. So Meep stands for MIT Electromagnetic Equation Propagation and is a free open source implementation of the FDTD algorithm. It's freely available online at the link that has been posted here. Meep includes several basic and more advanced features, including support for describing anisotropic, nonlinear, dispersive electric and magnetic media. It provides a set of different boundary conditions. For instance, boundary condition to express symmetries, so we can save part of the domain by using symmetry condition, and also boundary condition to express open regions such as PML or perfectly matched layers. When it comes to the computer science part of the Meep code, Meep provides support for running on supercomputer or a distributed memory parallelism, so allow us to divide the computational problem across different processes. It provides support for both Cartesian and cylindrical coordinates in 1D, 2D, and 3-dimensional geometries. Together with the calculation in the real domain, also provides a frequency domain solver. And of course, Meep provides a set of different routines for pre-processing and post-processing of the field computation. When it comes to the units, Meep use dimensionless units. That means that some units in Meep are automatically set to 1. So which are these units? Well, we have the electric and permeability constant in the vacuum that are set equal to 1. So once these two are set to 1, also the speed of light in vacuum is going to be 1. So when we express velocity in Meep, those will be all a function of c. So for instance, if we have a velocity that is 0.1 c, that means that the velocity will be 10% the speed of light in a vacuum. When it comes to the space units, so for the distance, the user can pick up any desired unit of distance that we call A. For instance, can be an SI unit, meter, millimeter, micrometer, such as A equal to 1 micrometer. Or it can be any typical length scale of a given problem. So for instance, if you have a scalar that is the size is equal to 3 millimeter, then we can fix A equal to 3 millimeters, and all the distances will be expressed in terms of this A that is 3 millimeters. So once we define the units for V, so we know that we normalize over C, and then we know A. So once we define the quantities for the velocity and the space, and then we can calculate what are the units for the times. So this will be the unit will be A over C, and dimensional, this is going to be a time, right? Because A is a space, right? And then velocity is a space over time. So this will be a time. So all the times units in Meep will be expressed A over C. From the time, then we can calculate the units for the frequency. That is going to be the inverse of the time. All right. So if times are in units of AC, So this will be C over 8. That is equal to 1 over T. So this is a frequency. Let's look at Meep's discretization, so how we discretize the simulation domain. So Meep used the standard E-grid discretization that we saw in the previous lecture, using the stagger grid. Meep includes a two coordinate system. So the standard E, right? So we divide our system when we have grid, and then remember that the E field and B field are defined on the stagger grid. So we were going to have a definition of our quantities within the grid, and this is a discrete grid. Meep also provide so-called continuous coordinates that give us the feeling that the space is continuous and is physical. So how this is work out? Well, so given a discrete space like a cell, Meep allow us to calculate the values of the field that is actually defined only on the grid nodes by interpolating the quantities defined on the different nodes. So in this case we have 4 values, so we have F1, F2, F3 and F4. What we are doing, we're taking these 4 values, and depending on the distance we make a average weighted average of the different values of F1, F2, F3 and 4. So we take this value, and then depending on this distance we calculated the values at this point. So any point in the domain, so for instance here or here, we can calculate the values on this point by basically interpolation. And that's the basic trick that Meep uses to describe this continuous grid by using interpolation. Meep uses 2 primitives to express vectors and coordinates system. So one is a vec and the second one is called IVec. We're going to use a vec for expressing real values vectors. So these are vectors whose elements are real values in d-dimensional space. Right. So if we are in one-dimensional space, then d is equal to 1. What is the difference between vec and IVec? Well, the difference is that IVec is only for integer values, vectors. So, for instance, if we want to describe location in the E-grid, we are going to use IVec. In Meep, an FDTD simulation should occur within a finite volumes of space. So we have our simulation domain, that is our volume of space. In Meep, the simulation domain is called computational cell. And this might be confusing in the sense that we call cells, the small part of the grid. In Meep, by convention, we call the computational cell all the simulation domain that we work on. So in Meep, computational cell is all the simulation domain, is not the single cell. So this computational cell is equal to the simulation domain and is also terminated by certain boundary condition that we can impose. On supercomputer, when we're using parallel computing, the computational cell or the simulation device or the simulation domain is divided in big rectilinear chunks. So for instance, let's assume that we have a 4 processor, right? And this is our simulation domain. We can divide it in 4 big chunks, chunks 1, chunks 2, chunk 3, and chunk 4. And then Meep is going to assign to a different processor each computation belonging to this computation. So let's think that we have chunk 1, right? So we're going to have a part of the big arrays defined on this domain. So the Meep will assign to processor 1 all the computation that is relative to this part of the simulation domain. So in summary, Meep divides in big chunks the computational cell, and these chunks are assigned to a different processor. However, in this course, we are not going to deal with the supercomputers. In the future, you might want to use them, so you will need to come back to the concepts of chunks. When looking at the boundary condition, Meeps provide several user-selected boundary condition. For instance, we can use a perfect electric or magnetic conductor, where the relevant electromagnetic field components are set to 0 at the boundary. Meep does not implement any absorbing boundary condition per se, so we don't say, oh, just put here a boundary condition. What we need to do is to explicitly put an artificial material, a perfectly matched layers, within the boundary. So we will define a PML within the boundary to express open boundary condition. So let's look at the practical aspects for using Meep in this course. So the first step that we need to do is to install the Meep. What we're going to use is a Python interface of Meep that is called the PyMeep. All the instructions to install the PyMeep are available on this website. But let's look very quickly together what are the different steps. The suggested installation procedure is first to install Conda or Miniconda that are package managers for Python. Right. So the first step we need to install Miniconda or Conda. So you can find easily online the instruction on how to install the Conda or Miniconda on your workstation or laptop. After we install Miniconda or Conda, we run the command line conda create -n mp -c conda forge pymeep. This command is going to create a Python environment that is called mp. We can call it as we like it, right? So we can be meep Python or something like that. It doesn't really matter. So this will create an mp environment with all the dependencies of PyMeep. So we install PyMeep, and together with the PyMeep all the dependencies. So for instance, PyMeep requires the installation of other software, and this software will be installed together by Conda. Once we run conda create, we just need to activate our environment using conda activate mp. If you want to check if everything is installed correctly, you can just run this line of code, python -c import meep, just to check if it gives any error, or you can try to run some of the tutorial examples that are provided in the Meep GitHub page that is linked here. This is the last slide of this lecture, and talk to you soon.